Good morning. Myself Dr. Palash, Associate Professor, Department of Chemistry, Semester of Science and Technology. Today, I'll be talking about stereochemistry, which is basic part of organic chemistry. So, I'll touch upon different types of stereoisomers, optical activity, optical isomers, asymmetry, chirality, enantiomers, diastomers, specific rotation, configuration, projection formula, Newman, Shor's and Fisher and their interconversion, chirality molecules with one and two stereocenters or without no stereocenters, meso configuration, racemic modification and their resolution, relative and absolute configuration, DL or RS configuration designation, geometrical isomerisms, cis trans, C90, EZ with CIP rules. So, when you talk about stereochemistry, so that starts with the isomerism. What is isomers? Isomers are same chemical formula with different structures. So isomers are two types, constitutional and stereoisomers. And stereoisomers, especially it is based on the 3D representation. And here it is divided into two parts. One is geometrical cis-trans isomer, another is optical isomers or that having asymmetric molecules. So when you talk about constitutional isomers, that means the molecules or isomers with different functional groups are there. So you can see ethanol, dimethyl ether, or 1-chlorobutane, 2-chlorobutane, or pentane, isopentane, or acetone, propanaldehyde, all having there is a atom attachment is different and we can tell constitutional isomers. Now, we are more interested in stereoisomers because in three-dimensional molecules are represented in three-dimensional, yeah, and in reality also they exist. So there are two types. One is geometrical or cis-trans isomer. So that is based on the restricted bond rotation over double bond or cyclic ring. So you can see here when in cyclobutane, bromine and chlorine atoms are there in the same in the above the plane. That means we can tell same direction. So that's it's called cis. When they are in one is above, another is below the plane, that means they are trans. Similarly, cis 1,4 dimethyl cyclohexane, you can see two methyl groups are above the plane, so that's why cis. And when they are in one above, another below, that is called trans. Similarly, the geometrical isomer is possible over the double bond. You can see that cis to butene and trans to butene, where hydrogens are same side and where hydrogens are opposite side. So same side means cis and opposite side means trans. So we can easily identify the cis and trans isomer based on their different physical properties. For example, boiling point of cis isomer 3.7 degree and it's a polar 0.33 dipole, whereas boiling point is 0.9 degree for trans isomer and it's a non-polar compound. Similarly, that cis 1,2-dichloroethylene and 1,2-dichloroethylene cis and trans isomer, you can see they have different. However, not all alkenes can give that cis or trans isomer because minimum condition is that single carbon atoms should attach with two different groups. So that's why they are not cis-trans isomer. Now, when you talk about conformational isomers, you can see that this dog is a stable conformation as usual we used to see. But have you ever seen this kind of conformations? That is very rare case. That's why it is called unstable conformations. But it is possible. Now, if we talk about configurational isomers, so this is the common, but this is very much uncommon because their originality is different. Because you see here, this tail is as part of leg, where leg is at part of the tail. So they have different configuration. Now, when you talk about chiral and achiral objects, chiral means so they are not mirror image, superimposable. So for example, right hand and left hand, or right ear or left ear. Okay, so they are chiral. They are not non-superimposable mirror image isomers. Whereas if we talk about chair, the spoon, glass, they are having the plane of symmetry. That's why they are achiral. So chiral, a molecule has to be chiral provided that carbon should be attached with four defined groups. So for example, 2-bromobutane. So methyl, bromine, hydrogen and ethyl groups. So this molecule is asymmetric and does not have any plane of symmetry. So compounds with an asymmetric center, you can see 4-octanol, 2-bromobutane, 2,4-dimethyl hexane. So they are optically active. Now, if that compounds, chiral compounds having mirror image isomers, they are called enantiomers, or they are called uh, non-superimposable mirror image isomers. So they are part of the stereoisomers, and enantiomers, they are called enantiomers. They can have similar physical properties. Sometimes it is difficult to separate out. Now, enantiomers basically they are non-superimposable mirror image isomers, and you can see that suppose this is 2-bromobutane, and you can see they are enantiomer pairs. So, chiral compounds have non-superimposable mirror image isomer, whereas achiral compounds they have superimposable mirror image isomers. They are identical compounds. Now, what is the difference between asymmetric center and stereo center? Asymmetric center means that carbon should be attached with four defined groups. So in this case, this carbon is called asymmetric center. Whereas stereo center means when you change one atom and replace with another one, and it forms that another stereoisomer, that is called stereo center. So in that way, asymmetric center may be stereo center, but not stereo centers. Not all stereo centers are asymmetric centers. So how to draw enantiomers? Basically, you need to put, this is a Fischer position formula, 2-bromobutane, and you can put the mirror image. You can get the corresponding enantiomers. Now, how to define this configuration? That is called absolute configuration. So based on that CIP rule, Kahn-Ingold Prelog rule, and that rule suggests that you need to go for selection rule based on its atomic number. So among these four, bromine having highest atomic number, so it should get first priority. Now among this ethyl and methyl, as first attachment is CH2, so you need to go for second attachment. So second one you get second priority, then methyl is third priority and hydrogen is fourth priority. Now the rule is when you go for 1, 2, 3, 4 in a clockwise direction and smallest priority group hydrogen in the down, then it is called rector or R. And when 1, 2, 3 is clockwise direction and hydrogen is down, then it will be, so this is S and this is R isomer. Okay, so sometimes we have seen that this molecule, so 2-butanol, you can see that hydrogen is the above the plane. So now if I go for 1, 2, 3 clockwise direction, but as the lowest priority group in the above the plane, so rule will be different. So clockwise direction, still it will be S isomer. Okay, and when you go for Fischer correction formula, when hydrogen is on the vertical line, then rule will be as it is. So you can see 1, 2, 3 clockwise direction, so it will be R, and this is 1, 2, 3 anti-clockwise direction, it will be S. So now when hydrogen is the horizontal plane, so you can have 1, 2, 3 clockwise, so it will be S isomer, and this is 1, 2, 3 anti-clockwise direction, hydrogen is horizontal plane, so it is called R isomer. Now, what is plane polarized light? First of all, normal light having in all directions, it will scatter. But when you pass the polarizer, then light, it will have a certain directions it will have. Okay, now when this plane polarized light pass through a sample, then the sample has the ability to rotate the plane polarized either clockwise or anti-clockwise direction, and based on that we can say that the molecules are dextrorotatory if it is a clockwise direction, and if it is anti-clockwise direction that can be called levorotatory, means plus D or L, plus D or L, D for dextrorotatory, L for levorotatory. So sometimes it has been observed that some R enantiomers are sometimes dextro, sometimes levo, or SI enantiomer, sometimes dextro, sometimes levo. So that doesn't matter because R and S isomers, that's based on the theory, and dextrorotatory, levorotatory based on the experimental part. So you can see here OH 1, 2, 3. Anti-clockwise direction, hydrogen is below the plane, so it will be S, lactic acid. Whereas sodium lactate, you can see here 1, 2, 3, anti-clockwise direction, so it is a S isomer. Now, if you want to determine the specific rotation alpha at constant temperature and wavelength, that is alpha observed divided by LC, that is your observed specific rotation divided by polarimeter cell length into concentration. So suppose one enantiomer specific rotation is plus 5.75, so another enantiomer has to be exactly negative, and that's why even if it is a 1:1 enantiomer, so that is called racemic mixture. And another term is called enantiomeric excess. When enantiomeric excess is determined, that is actually purity of one enantiomer than others. So that is determined by the observed specific rotation divided by specific rotation of pure enantiomer into 100%. So you can see that 40% enantiomeric excess, that suggests that it will be 70:30 ratio. Now, compounds with two asymmetric centers, when you have, that means 2 to the power n number of isomers possible. So you can see that 4 stereoisomers possible. So now when hydrogens are same side, you can tell erythro. When they are in opposite side, you can tell trio. And accordingly, we can have their mirror image so that we can get 4 stereoisomers. Now 1 and 2 are enantiomers, 3 and 4 are enantiomers, but other combination 1, 3, 2, 4, 2, 3, they are diastereomers. Now, the same concept, when two asymmetric centers are there, we should have 4 stereoisomers. So suppose C is 1 bromo 2 methyl cyclopropane, or trans 1 bromo 2 methyl cyclopentane. So you can have corresponding its mirror image isomers. So C isomers having enantiomers, trans isomers having enantiomers, and then C and trans combination is their diastereomers. Now, identifying an asymmetry center, how to identify? We need to find out that 4 defined groups are there. So we can have 4 defined stereoisomers. But when we don't have asymmetric center, for example, in this case, when two attachment is same, so they are called asymmetric molecules. So sometimes there are two asymmetric center, but 3 stereoisomer is possible because there is a possibility of mesoisomers. Okay, so mesoisomers having the plane of symmetry, we can see this. This is your example of mesoisomers. So that's why it has only one molecule. So basically, this enantiomer and its another enantiomer, mirror image enantiomer are same. So that's why 3 compounds will be there. So because they are superimposable mirror image isomers, that's why they are having 3 structure. They have, sometimes they have plane of symmetry, so that's why they are optically inactive also. Meso compounds are optically inactive because of plane of symmetry. So you can see that molecules having plane of symmetry. So this is meso compound, but this enantiomers cannot be meso compound because plane of symmetry is not there. So this is a plane of symmetry, but this is not. They are enantiomers. Now, how to represent chiral compounds? So there are 4 ways: Fischer projection, flying wedge, and then Seuss and Newman projection formula. Suppose in these molecules, chlorine is on the plane, bromine on the plane, methyl is above the plane, and hydrogen is the below the plane. That means here wedge structure is this thicker bond which is above the plane, and hedge structure is dotted line that is below the plane. Now, when you talk about ethane in three-dimensional structures, so basically it's a wedge hedge structure where we can see that C1 and C2, that protons having some kind of interactions. Now, in a Fisher position formula, that is a two-dimensional representation where the molecules fragments, molecules main fragments, it will be in the vertical line, where there will be horizontal line. Some functional groups will be there, and it is highly applicable for carbohydrates. And if you see here in this case, bromine, hydrogen, amine, and cyanide. So bromine and hydrogen up and down in a vertical line, whereas in H2 left side and cyanide in the right side, and you can show that hot to Newman prediction formula. Now, when you talk about Schwarzschild projection formula, that represents that interaction between two successive atoms, okay, groups on adjacent carbon. So if you see the molecules, okay, so two methyl groups are close to each other at 0-degree angle. It's basically super impossible. So in that case, this bond angle is 0-degree, and you can see the eclipse structure. And when there is a 60-degree bond rotation, then this axis repulsions will be minimized, and that will be called staggered conformation. The Newman projection formula, that is also possible for conventional relationship and to show the interactions, and it will show what kind of steric hindrance is possible. So there are what is the way to write the Newman projection formula. So here one rear carbon will be there, one front carbon will be there. In the rear carbon, you need to put the molecules with circle with the three different groups, whereas front carbons you need to put it in a Y-shaped geometry molecules. So you can see hexane, here ethane, and you can see that molecule is fully eclipsed conformation. So conformation be shown by bond like projection. So you can have this bond line, then Schwarzschild, and then Newman projection formula. How it is forming it? You can see that OH is up, hydrogen, bromine down, and then methyl is down, hydrogen and chlorine is up. And corresponding Newman projection formula, it is much easier through Schwarzschild. So you can see OH, bromine, hydrogen, and HCl. So bromine, methyl, OH, bromine, methyl, hydrogen, chlorine, methyl. Yes. So that's what the Newman projection formula. Now the same molecules, we can have this Gauche, we can have anti, we can have other conformations. So anti-conformation will be that is the 180-degree angle difference between the similar groups. Now if you see the molecules, suppose this is the molecules. So if you see that this is the left side, this is the right side. So we can have aldehyde and up CHCl, bromine down, and methyl. Now if we can show CHO, HCl, then OH pair, and methyl, and that's what the final answer it is. Now Fisher projection to Schwarzschild projection, how to do that? So basically you can have this tartaric acid where C3 C4 rear carbon, 1 2 are front carbon. So if we just OH, H, CO2H, CO2H down, hydrogen, OH, CO2H. This is ellipse conformation. Now you need to rotate by 180 degree so that carboxylic acid will go up, which is go down, and hydrogen left side. So you can have this staggered conformation. Similarly, when we have 2,3-dibromobutane, you can show that this is a um, hydrogens are in opposite side, rare carbon. It's a Fischer reaction formula. Now, if you have this kind of compound, so first work will be you just make the Newman reaction formula. So you need to rotate amine, chlorine, and methyl. So OH, Br, phenyl, methyl, chloride, and amine. Then you go for that particle plane, right? Now, if you just turn over, you should get phenyl, OH bromine, NH2Cl divided by pH. Now this is the case, erythro case. You can see that more each functional groups will be in opposite side because this H OH CH2H H OH CH2H I have having, and then CHO OH so HOH. Now if you just rotate the molecules, OH hydrogen, then CHO will go up. Okay, so similarly, Fischer projection formula to flying wedge formula, you can see the molecules, uh, hydrogen and bromines, they are on the plane, and then carboxylic acids and methyl carboxylic acid down, and methyl is up, or carboxylic acid down, up, methyl down. Flying wedge projection to Fischer projection, you can see that acid and methyl group, bromine is right side, hydrogen is down. So how to resolve raceming mixture? So this involves mechanical separation. Suppose crystals are big enough, they can be separated using microscope. Crystal of the two forms have different shapes separated by magnifying lenses and forceps. This method is firstly used by Pasteur, the resolution of sodium ammonium tartrate. This is time consuming, and every compound cannot be crystallized at room temperature. Perfect crystallization, the method involves seeding of a saturated solution mixed with pure crystal. The, the solution now becomes supersaturated with respect to added NaCO and begin to crystallize. Biomedical separation, that is based on the principle Pasteur. Louis Pasteur. So this is the certain microorganism. It will take one of the enantiomer, whereas other enantiomers it will be rapidly then grow. And then column-tropic separation. This racing mixture can be separated by chromatographic or optically support. The diastomers absorbs which are formed have different stabilities. The one enantiomer will be held together by other that will be eluted first. So what is the best method? Best economic method is the diastereomer. So suppose you have the mixtures, then you take the chiral reagent, then it will react with suppose RR and RS. So it is the intermediate species. So they will have different physicochemical properties. So they will be separated out. Once that RR and RS isomers are there, we need to just crystallize out. So what are the compounds or chiral compounds are there? Hexaamine. So this is two amino, one butanol, one phenyl, two propionamine, quinine. So all these compounds. So if you want to resolution of racemic base, so you can have tartaric acid and treat with this camphor. So you can have monoethoxyethanoic acid and 3 beta oxy 5 ethanoic acid to resolve. So we can have the corresponding racemic alcohol with the carboxylic acids, and then we'll take the molecules for and if the diastereoisomers are we need to treat with these brucine molecules so that these acids will be getting deprotonated. Similarly, 3-hydroxy delta 5 electronic gate that is also forming the salt. Then once they form the salt, they will have different physical properties. Then followed by hydrolysis, you will be getting the dibutanol and L-butanol. So lastly, we'll be talking about Kahn-Ingold-Prelog rules, that is for absolute configuration of molecules. So that they suggest that if you want to know about the absolute configuration of a chiral molecules, first of all, higher atomic number will be get first preference, and lower atomic number will get the last one. Second, the when you have the higher isotopic mass, that will be preferred. When you have same atoms, then you go for the second atoms. So if everything is fine, 1, 2, 3, 4, it moves in a clockwise direction, and hydrogen lowest priority group in the below the plane. That means it will be R. Otherwise, it's saying isomer. So you can have the CH2Cl will get more preference than the methyl or ethyl or ester. So when we have cis-trans isomers, two carbons is pair in non-identical substituents. So when we don't have the lowest priority group, hydrogen hydrogen, then this compound can call cis, whereas these compounds cis trans both will be there. So this is trans isomer. Cis trans thus refers to relative configuration of the identical molecule. The absolute configuration is denoted by RS. Similarly, here two cases where cis-trans isomer is not possible, so you need to apply either Z or E, right? So in this case, 1, 2, 3 R, so it will be S isomer. Similarly, here you can see that molecules are too many possibilities will be there. There are two carbons, so total 2 to the power 8, 2 to the power 2, or 2 to the power 4. So you can see the molecules are highly flexible and aromatic. Now, when you talk about cis-trans isomers or geometrical isomers, it is not applicable to the single bond because the bond rotation is possible. Whereas double bond, it will have different conformations, and accordingly, bond rotation is not possible. For example, when BB are there similar, or BB is opposite, so you can have the cis-trans isomer. So 3-hexane, starting from C3-hexane, we can prepare cis-3-hexane and trans 3-hexane. Even if you have the cyclodeacane system where trans dicycloalkene is possible. So for this reason, we are assumed we omit the cis when the names cyclohexane with cis configuration is assumed. So looking for cycloalkanes containing 8 or more carbons in non-omega names would indicate the alkene simultaneously. So when you have bromine, chlorine, fluorine, methyl, So here bromine and fluorine having bromine having higher authority, and chlorine and methyl chlorine having higher authority. So basically, bromine and fluorine, bromine having higher atomic number, fluorine and methyl they will have higher atomic number, so it is a Z. So therefore it is impossible to use C star transformer, either E for anti and G for zebra. So is a nomenclature we can see that chlorine and methyl 1 and bromine and hydrogen 1. So basically they are C's isomer. Similarly here it will have 1, this is 2, this is 3. So you can see here, first of all, this is not a symmetric molecule, and only this is the case where it will opposite 4E, and this is the case where 6E will be there. 4E, 6Z. Oh, this is the similar. Now, Alene is the last topic, that cumulin, diene. So basically, this molecule is not a planar because there is a bond angle strain between 60, 30, and 40. So Alene is not a planar structure, but here the two atoms attached to the terminal carbons will be getting undercover. So if you have the monosubstrate or disubstrate monosubstrate cannot be optically active, whereas disubstrate it is optically active. So if you see that acyl diphenyl acetylene kind of alene system, and they are optically active. And if you have chiral alenes, then A equal to B should be there.